Hi everyone, welcome to this recitation on Pytorch basics. If you've done any kind of neural network training before, you are probably familiar with what I'm going to talk about today. So just skip ahead to the next one. But if not, then this is a quick overview of Pytorch and how to use it to train simple types of neural networks. So let's get started. And as usual, all our programming will be done in Google Colab. So open a browser and go to colab.research.google.com. So this should be free for you to access, and then just open a new notebook. Okay, so this should bring you to a blank Jupyter notebook. It's typical to use GPUs to train neural networks. So you might want to change your runtime type to GPU accelerated. So just do that and then connect to a runtime. Once you do that, you should be ready to start programming. It may also be helpful to rename your notebook to something sensible, like demo one. Good. So I'll assume that everyone is familiar with Python. So I won't go into the details of Python in this demo. You can try and train neural networks in Python from scratch, but that turns out to be somewhat painful. But fortunately, there are many well-established software libraries which can help ease the process. I like something called Pytorch, which is built upon an early library called Torch. But you should be aware that there are many, many others, including popular ones such as TensorFlow and JAX, both of which I'll encourage you to explore at your leisure. But for this demo, we'll be exploring Pytorch. Okay, so let's just begin. And as usual, let's import a bunch of basic libraries. So we'll import NumPy and we'll import Torch. We'll be training neural networks involving image data sets today. So let's also import something called Torch Vision, which will let us do basic image processing in Torch. Okay, so the main idea in Torch is that Torch believes that everything is a tensor. Okay, what's a tensor? A tensor is a multidimensional array. So the native data type Torch is a tensor. So here's an example. So let's just see how that works. So if I generate a random matrix, something like this, and I convert it into a Torch object. Okay, so if I convert it into a Torch object, so the from NumPy method takes in a NumPy array and makes it to a Torch array. And if we print these quantities out, you can see that A is a regular array. It's like a 2x3 matrix. But then B is a Torch tensor. Okay, so another point to note is that Torch stores all floating point numbers in float 64. Okay, so why tensors? So the main intuition is that tensors enable intuitive and efficient matrix multiplication across different indexing dimensions. And as we'll see very soon in a later lecture, the process of training neural networks involves a lot of matrix multiplications in weird dimensions, and this is really eased up by the use of tensors. The other thing about Torch tensors is that they can be natively differentiated, so they support differentiation by design, and we'll see why this is important when we talk about something called backpropagation in deep learning. So let me illustrate what these things mean. So let's create a few Torch tensors. So let's say I want to do something like y equal to ax plus b. So I'll create random random variables a, b, and x. I'll compute y equal to ax plus b. And I also want to compute sort of dy by dx. So I'll make sure that differentiating with respect to x is enabled. Okay. So let's calculate y equal to a times x plus b, and this is the usual numpy multiplication, but in Torch. So Torch dot macmul a x plus b. Okay, so print y. So I get some quantity. It's great. This is just some random numbers. So y is a function of x. Let's just also compute, let's say, to do other things with y, for example. So if I say z equal to, say, y dot sum, so this just sums 0.8 and 0.5. So y dot sum. So I print z, it should be something like 1.3. That's what it is. Okay, so z is now a function of y, which is a function of x. So I can, in principle, compute dz by dx. The way the Torch does it is to use the chain rule in a very clever way. We'll talk about the internals in a couple of lectures from now, but we'll just implement this here. So if I want to compute dz by dx, all I do now is I don't have to do anything algebraically. I just call z dot backward. It's the backward pass in some sense of this function. And once I compute z dot backward, I can now compute dz by d any variable that supports differentiation. So in this case, it will be x. So if I print x dot grad, it's just print x for now. So x is a variable, right? And now I can also print dz by dx with respect to each of x's arguments. So that's just x dot grad. Okay, so x is some tensor, some random numbers, and then dz by dx is 0.5 and 0.8. Notice that 0.5 and 0.8 were precisely, well, actually, I cannot read it out, I don't think. Oh, that's fine. Yeah. So it's some quantity which evaluates to this for this particular example. Okay, so that's 5-minute overview of algebra in Torch. So let's just get to it, and then we'll train some neural networks. Okay, so what we'll do is we'll actually not train real neural networks right now, but we will train a very simple sort of logistic regression model. And as we discussed in class, simple models such as linear and logistic regression can be viewed as one-layer neural networks. It's actually going to be the same if it's one or more layers. So we just train a simple logistic neural network right now. Okay, and the way we'll do this is we'll first get some data. So we'll train a logistic classifier on a training data set called fashion MNIST. So fashion MNIST is similar to the very popular MNIST data set that's used in machine learning all over the place. Considered to be slightly more challenging, but it's kind of similar. It's basically grayscale images of a small size. There are 10 different classes, and each class corresponds to different items of clothing. Okay, so we'll download this data set. So fortunately, Torch Vision already has a method that lets us do this quickly. So we just download using that function. So let's download the training data set. There's also an associated test data set, which we'll see how that works. So we'll download first the training data set. Now notice that the format which we require our data is in the form of Torch tensors. So let's also just take the data set, which is basically a bunch of images, and convert it into Torch tensors. Okay, so I'll just off the bat make it into a tensor. Okay. So similarly, we'll also just download the test data sets, which is disjoint from the training data set. Okay, but it's also standard. So let's just download both of these, and we'll save it to the fashion MNIST folder in our drive. Okay. So that's it. So So let's do that. It'll take a couple of minutes. Was a runtime error. Dataset not found. Why? Oh, I need to do download equals true. Sorry. Yeah. Also, it's not already downloaded, so I need to download it the first time I call this function. So cool. Okay, there you go. So it's downloading the data set, and that was quick. Okay. So let's quickly check whether things have been downloaded. So I'll just print the length of train data. Should be approximately 60,000 images. That's the train data set. About 10,000 images in the test data set. So let's see. Yeah, 60,000. Okay, good. But this is the same size as MNIST. Right? So that's by design. Okay, let's also see how the images actually look like. So I'm going to look at, let's say the first image. Okay, so train data of 0. So the first image. What's the size of this image? Let's see. And what's the label? Okay, so size is it's a 28 by 28 by 1 image. Okay, so it's one channel and 28 by 28, and the label is 9. Okay, so what does 9 mean? Let's try and see what that image looks like. So can't really directly plot the image itself, because remember that it's a torch tensor, right? So let me convert that into an image and then into a NumPy array and then plot it as an image. So for plotting, we'll use matplotlib. Okay. So this standard command, and now I'll plot the image. So I can use I'm sure. So it's a tensor of size 1 times 28 by 28. So let me have to squeeze that singleton dimension out. So I'll squeeze it out, and then I'll convert it into a NumPy array. Okay, so let's see what the image looks like. And it looks like a shoe. It should look like a shoe. Okay, so each class in Fashion MNIST looks like a different piece of clothing. Let's see a few more images just to get a sense of the data. It's always good practice to visualize the images or any data that you're trying to classify before actually training a model. So let's just visualize how they look like. The nice thing about Torch is that it lets you step through big data sets very easily. So for that, we have to construct a data loader. So let me construct a data loader object. Okay, so that in this case, a training data loader. What this does is it helps me sequentially step through batches of training data points. Okay, so this is a method in Torch, torch.util. So I'll load the data loader. Okay, and so this is going to basically chunk up the training data into different batches. So I can specify the batch size. So let's say 64. It's pick with what a reasonable batch size. It's also common in neural network training to randomize the order of how you read the data. So let's shuffle the data. Shuffle equals true helps you do this. Similarly, we'll also have test data loader. This is the same thing, except that we are stepping through the test data. Okay. And this, again, this need not be the same batch size, but just for ease of use, let's just do this. Now, in testing, we don't need to really shuffle anything. It's not necessarily the same. So we'll just do shuffle equals false. Okay, so let's create these two objects. Oops. Which is now what utils. See how this works. Okay, so we constructed these objects. Now we can call these objects to spit out of a few images, like a batch of images. So let me show how to do this. And this is very easy. We just iterate through the data loader. Okay, so you can do the same thing with test data loader, but let's just do an example with train data loader. So we can iterate through the next batch of examples. Okay, so now image and labels have a batch of 64 training data points and labels respectively. So we'll see how they look like. So let's just plot a few. So let's just make sure that the images are kind of big, so and the same size. So for index in say, I don't know, let's just do say 8 images. So 4. Okay, so I'm going to just plot 4. Let's say 4 images. So this one. And then show images. Again, I need to make sure that they're converted to NumPy array. So as usual, squeeze the single dimension out and then convert it to a NumPy array. And if I want to plot in grayscale as it should be plotted, then let me also change the color map to see what this does. Oops, images is not defined. Image, sorry. Okay, I should have said images. Let's say image. See, I have to not define. Okay, so you see some images here. It's a shirt. You can see 2 shirts, kind of like a shoe and like a handbag. Okay, that's good. So these are the different classes. There are 10 different classes of clothing items, and the classifier will learn to classify these different types of items. So let's train our classifier. Okay. So as I mentioned, we will do a simple logistic regression, which is basically a linear model with a cross entropy loss, right? So let's set up the model. It's it's kind of simple. So one thing to keep in mind is that Torch is object oriented. So everything is a class, right? So you define classes and methods of different classes and so on. And this is useful because in defining a neural network, you have this the modularity property, right? So you can define networks from smaller networks and so on. So object-oriented definitions make the most sense here. So I'm going to define a linear regression class. So which is basically a Torch module, right? So any Torch module that you define has to have an init method. Okay, so this is just boilerplate code which you'll have to plug in at the beginning of any net model definition that you make. So it has to have an init method. So I'll also have a linear method. Okay, so self.linear. So this is going to be basically a linear layer. Okay, so Torch has all kinds of layers defined inside it. So I'm going to have a linear layer. So a linear layer in this case is going to take the input, which is a 28 by 28 dimensional array, an image, 28 by 28 image, and then classify it into 10 classes. Okay, so this is the Torch linear layer. So while setting up models in Torch, you also have to not only set up the layer itself, but define what the layer does. So what does this linear layer do? So I have to only specify the forward pass through this model. Okay, so because as we discussed before, backward passes or derivatives are natively handled. So I only need to define the forward pass. So what does forward pass do? Well, the forward pass takes an input x, okay, and then multiplies it with the linear operator, right? That's all that does. Right? That's all you need to specify here. So it takes an input x. Now x is image, right? So I need to first flatten it. So that I can do using extra view command. So it flattens it, removes a singleton dimension, and makes it into a vector of size 28 by 28. Okay. And then I apply the linear operator. Okay, so I transform the input via the operation specified in sub.linear. Okay, so it's a matrix multiplication with matrix size 28 by 28 times 10. And that's it, right? So that's all there is in a linear. It's really simple. So that's all you need to specify for a linear here. Okay. So as simple as this. So this is a single layer network. This is the operation of a single layer network in Torch. Soon we will see examples of more complicated networks. Okay, so so in class we discussed a three-step recipe, right? So we had a representation. So here's a representation of the network. So that's step one. One thing to note is we'll also use GPUs. So let's construct the net object, the neural net object, and send it to the GPU. So that can be done using the CUDA method. Okay, so I'll send the net, I'll construct a net object and send it to the GPU. So that's step one. Okay, so I constructed a neural network. So this is the representation of the machine learning model we're going to train. But then we also have steps 2 and 3. So step 2 will be the definition of a measure of goodness, or the loss function. Since we're doing logistic regression, we'll use the cross entropy loss. So it's also implemented in Torch. So it's the cross entropy loss. Okay, so that's step 2. That's all there is to do in terms of step 2. And then step 3 will be the method to optimize. Okay, so we need a method to optimize for this loss. So we will define the optimizer, and of course here too we can define various choices of optimization routines. We'll talk about several in the next couple of lectures, but for today we just do simple gradient descent. Okay, and so that is also implemented in Torch. Actually, technically, what we are going to do is batch gradient descent, because we have specified a batch size of 64. So we're going to do batch gradient descent, and if you don't know what this is, we'll talk about it soon. Okay. So that is implemented in Torch by a routine called SGD. I find this name very troubling because SGD has different connotation, right? So it has a connotation that so the stochastic gradient descent is called SGD, but Torch calls any gradient descent SGD, which I have slight issues with. But that's fine. So be aware that the Torch SGD is not nothing stochastic going on there. It's just standard batch gradient descent. Yeah, you specify what the batches look like. In this case, in fact, our batches are shuffled, right? So it is actually the same as SGD, but let's not get into that right now. Okay, so we're just going to do a regular gradient descent. For gradient descent, I need to specify a learning rate. So I'll just specify some learning rate here, and that's about it. So that's a three-step recipe of machine learning. But in some sense, this is all we need. I mean, these are the main components of Torch. So in later lectures, everything else will be the same. The data loading will be the same, and what we're going to do next is going to be the same. Really, all that will change is the stuff here. Right? We're going to make networks more and more complicated as we go along. Okay, but this is basically it. Right. So the rest of the demos is just going to be like basic bookkeeping kind of stuff. So we'll see how to visualize train and test error and so on. So let me just set up these. And if you've done again any amount of machine learning before, these should be standard, right? So we typically define a model, train a model over some number of epochs. So here let me just do like 20 epochs, and then keep track of train and test loss and see how they are behaving. Okay, so let me just look at that. So each epoch will go through the entire data set Okay, so I will step through the data set, and again, this we can easily do using the data loader object that we have defined here, right? So we can step through the data set. So I is the index, and data is the batch of data we're going to pick up. Okay, so let me grab the images and labels from the data. Okay, these are already Torch tensors, as you may remember. So we need to send them to GPU first, because we're doing training on the GPU, right? So the network has been sent to GPU. So let's send our data to the GPU as well. Okay. So now we need to basically update the weights of the model by backpropagating through backpropagating the predictions of this patch through the network weights, and then taking a gradient step. Right. So that's all we need to do. So this is done using a few commands here. So first we zero out the gradients. So gradients accumulate with different data points by design. So let me zero out the gradients for each batch. Okay, so for each batch, I'll zero out the gradient. Okay, so I'll zero out the gradient and do a forward pass first. Okay, so I'll forward pass all the images in this particular batch through the current model. Look at how well the current model predicts the labels. Okay, so I'll compare the predicted output with the labels, and then use this fit, which this is the error in the prediction, and I'll backpropagate the error through the model. Okay, so that's fit, not backward. So this is it. So this will compute the gradients of the output prediction with respect to each of the weights. Okay, so that's all there is to it. And once we do that, we take a step in the direction of the gradient. Optimizer step. Okay, so this optimizer basically contains all the parameters of the network, and step basically takes a step in the direction of the gradient times the learning rate. That's basically all there is to it. Okay, so just for bookkeeping purposes, I'll also keep track of the training loss. Cool. So this is basically the training. It is also beneficial to keep track of. This is not mandatory, by the way. You don't need this to train your model, but it's helpful for monitoring purposes, to monitor overfitting and so on, to see how we are performing on the test data set as well. So I'll do the same thing with the test data set, but here I will make sure that I don't take any gradient steps. That's all, right? So I don't want to train on the test data set, right? It's not allowed. So I'll not take any gradient steps. And this you can do with Torch.low-grad. So exactly the same steps as above, except that I'm not computing any gradients here. Okay, so exactly the same steps above. I'll send the images and the labels to the GPU, and just measure the predicted output and see how well they do. The predicted output is net of images, and then compute the loss on the test data set. That's all. So there's no optimizer step and so on, because I'm not taking any gradient steps. I just measure the test loss, keep track of it. And that's basically it. That's all there is. So this is two two loops. So there's an inner loop which enumerates through the data loader, and there's an outer loop which runs different epochs. 20 epochs should be enough in this case. We'll see. Okay, in the end, we'll just measure the total train loss. Okay, so I need to average over the number of data points, but remember that I'm enumerating, through different batches, right? So I have to normalize by the batch size. So just to make sure that my number is between 0 and 1. Okay, so otherwise you'll have a multiplication by the batch size. Okay, so this is it, and then just keep track of the history. So store this in history. Okay, that should be it, I think. Let's see if this works. So print, let's print various things. Epoch, check train loss. So again, boilerplate stuff. Test loss. Percent epoch. Loss. This is the instantaneous loss. See if this works. So this is basically. Oh, sorry. This has to be within the outer loop, I think. Okay, this should work. Let's see if this works. I hope I got my Python indentation correct. Let's see if this works. Okay, should take just a couple of minutes here. Let's see, inner loop happening. So it starts off with a reasonably high loss as expected, right? So ideally, your loss should be close to 0, right? It's a binary logistic loss, so it should be close to 0. Not 0 yet, but as you can see, it's already starting to go down. Train and test loss are both down, and this will, let's see how far I can push this. You can see that they tend to hover. After a while, they just kind of track each other, which is fine. It's reasonable to expect train and test loss to be approximately the same with each other. That's what you would see in kind of unbiased data set. Okay, so let's give it a couple of minutes here. So while it floods, maybe just a quick recap of what we did. The three main ingredients would be the data loader, right? So set up data loaders for stepping through your data sets, the model representation, and so the three-step recipe, and the model representation, the loss, the optimizer. This is really the heart of everything that we're going to do. And then the validation part, so seeing how the model works. And here you have to be careful of a couple of things. One, be careful that you remember to send. If you're using a GPU, you don't have to use GPU, by the way. It's just a bit slower if you don't use a GPU. But if you are using a GPU, remember to send your data to the GPU using the CUDA command. And so use the so within each epoch and within each batch, use the backward command to compute gradients and the step command to take gradient steps in the parameter space. That's about it. And let's wait a couple more minutes before we're done. As you can see, let's see how we are doing. So it's kind of going down. It's not great. 0.46 is not great. It's not bad either. I mean, it's definitely far better than chance. So 0.45, 0.46, that's about as much as you can do in so many epochs of training with a single layer logistic regression model. And that's the training loss. The test loss is hovering a little bit above that, which is also to be expected. Okay, so while it's winding up, let's just see. Okay, so I think it's done. So let's just plot them to see how they look like. I mean, we can already see it, right? So you know how the losses evolved. So to visualize this, let's just plot the training and the test error. Train and test loss are in these history variables. So just plot them. The same plot. Okay, so I'll see how they look like. Okay, we just label the X and Y axes as well. Plus, let's see. Oh, something happened. Oh, it just. Yeah, that's what we do. Okay, good. Okay, so orange is test error, blue is train error, and they kind of track each other. So things are good. If you have the patience, you can train for maybe 50 epochs and see how that works. But that's about it. Okay, so let's just wind up by just making a few. These are loss curves, right? But are they actually making sense? So let's see if they make sense. So let's just actually look at some images. Okay, so I can maybe predict I can use my network. So my trained network has the parameters, right? So I can maybe predict the labels of some batch of images. Okay, this is the last batch that was stored in images. Okay, so how do I look at the labels themselves? Well, I look at max. So the predicted output, remember it's a logistic regression, so I need to, so it produces a probability distribution over labels. So the actual class label is the argmax of the probability distribution, right? So torch.max gives me the labels, and I can print the true. This is a predicted labels, right? I can print the true labels as well. See how they match up. Okay, so as you can see here, so the true labels are 327584, and the predicted labels are 317582. Okay, so there's an error in the second image, and there's an error in the sixth image. Okay, so sixth image is not class 2, it's actually class 4. What about the rest? 56891, 56891, 91815, 91815. Oh, that's great. So in this particular batch, there are 2 errors being made, which is not too bad. Actually, let's see if I'm curious to see what the errors are. What do the actual images look like and which errors are made? So let's just display these images. So maybe I'll display the first 6 images. Okay, so let's see how they look like. So just visualize the actual images. It's just good practice to debug, see what's going on, right? So let's see if the network is making obvious mistakes or whether I just plot all of them. Let's see, so many other 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 images in this batch. I'm going to just show all of them. So let's just display all the images. Let's see. Just index images is on the images is on CUDA, so I need to bring it back to CPU and then convert it to a NumPy array. Okay, so let's see what this color map says. Okay, so second, oh, sorry, that's why this the error. Okay, let's see if this works. Okay, so image number 2 and image number 6 are being predicted. Image number 2 is label 2, but it's being predicted as label 1. I don't know what these labels mean, but it's actually interesting, right? Because you can see, I don't know, does this, I assume this is like a shirt, but does it look like a shirt? Maybe not. Similarly, I assume this is, I don't know, a sweater maybe, or something else. I don't know, maybe there's some confusion here. Anyway, so yeah, these perhaps would be errors that even a human might make. We'll see. But the others seem quite distinctive pieces of clothing, and it's nice to see that the model is also learning the concepts quite well. Cool. So that's about it. That was a brief overview of Pytorch and also how to use Pytorch to train simple neural networks. In the coming lectures, we'll dive quite a bit deeper into more interesting types of networks, as well as more interesting applications of neural networks and how they're used in practice. Thanks, everybody. Take care and see you next time.